Okay, so in this video, I would like to prove that every PID is Noetherian. So to start off with, I'm going to assume that we have any PID, and we'll just call this R. And this is a principal ideal domain, so this means that every ideal in this ring is principally generated, so it's generated by only one element. And so I'm going to claim that, we can actually prove that this is Noetherian directly. So what I'm going to do is I'm going to assume that we have any ascending chain of ideals in R. So I'm just going to call these I1, I2, I3, and then so on. And we want to prove that this eventually stabilizes. So we want to prove that for m large enough, basically, Im is equal to Im plus 1 is equal to Im plus 2, and so on and so forth. Okay, so, and I'm going to claim that we can do this using kind of a clever observation using the fact that R is PID. So the main important step is that I'm going to look at the union, call this just the union over n of all of the In. And because these ideals are nested, so because I1, I2, I3 are nested, this is actually an ideal. And maybe you could try proving this for yourself. If you want to get started, you could maybe start by assuming that like A and B are two elements of this. So assume that A and B are in this union of In. And then what you could observe is that, A is contained in one of these ideals. So maybe it's contained in like I5 or something. And then B is also contained in one. But because the ideals are nested, A and B both have to be contained in the same ideal. So there has to be an ideal somewhere in this chain so that A and B are both contained in the same ideal. And using that, you can prove that this union is an ideal. Okay, so but remember that R is a PID, and so this union actually has to be principally generated. So this is generated by one, I'll just call it D, that's in this ring R. Okay, and so now we want to make a clever observation, right? So because D is in this union, and so in particular, D has to be in one of these ideals. So maybe D is in like I100 or something. But we know that D is in one of the ideals, Im. And this actually means that the ideal generated by D is a subset of Im. Because if you take any multiple of D, it still has to be contained in Im. Okay. So we have basically two things here. We have that the ideal generated by D is a subset of Im, but then we also have that this is a subset of Im plus 1, and that's a subset of ... And all of these are subsets of the union of In. And remember that that's just the ideal generated by D. So simultaneously, this ideal is a subset of Im, but then Im is a subset of this ideal. So the two sets have to be equal. And so this is the key step in this proof, that now we know that Im has to actually be the ideal generated by D. And that actually implies that Im is equal to Im plus 1 is equal to Im plus 2, and so on, because you can apply the same argument, basically in each case. So yeah, so that gives us that Im is equal to Im plus 1 is equal to Im plus 2, and so on. And that's it. We're done.